Good morning, ma. Guru, how many people are there?
19, sir.
90. So today we'll start with a new topic and try to finish off this topic in today and next class, maybe Wednesday, right? So we'll try to finish off and then start the third unit because we need to cover still long units. I think principal sent a circular to start the regular classes, that is physical classes from 6th. I think the timetable will be shared with you by the HOD. I think it's not at finalized. So it will be hybrid. Some days you will be coming here and some days you will be in online. I think the lab classes will be scheduled in such a way that when you come here, you do the lab. That's what I'm thinking. I'm not sure. So anyhow, this week I think they will finalize and then give you the schedule, right? So the timetable may change. So accordingly, we have to adopt. Okay. So let us, last class, we are discussing about the problems and in autocatalyzed reactions, this design of reactors for a single reaction we did for what type kind of things, whether PFR or MFR or a combination, what will we give you the best volume of reactors for a particular rate, right? So we'll go for the next set of reactor is a very good reactor that is called as a recycle reactor. What does this recycle reactor means? It's a neither a plug flow reactor nor a CSTR nor a batch reactor. It is a continuous reactor where you are keeping a plug flow reactor. In plug flow reactor, what is the what do you call general criteria of plug flow? There is no actual mixing in this direction. That is, along the length, there is no mixing, and if any mixing will happen, is only in the radial direction, that radius, right? That is what is the main important point of plug flow reactor. So a recycle reactor is not like a plug flow reactor where there is no recycle. Neither it is a CSTR where there is a complete recycle. So we assume there is a plug flow reactor. The plug flow reactor is having an inlet and outlet. From the outlet, some of the stream, which is converted product, will be taken out. That stream, let it be some R, right? So the fraction of it is R, which is called as a recycle fraction. We'll see what is that. So here the stream branches into two. More of it will go as the product. Some fraction of it, that R is based on 0 to infinite. It goes as a recycle and join in the inlet, join at the inlet and then goes. So what will happen if R is 0? R is 0 in the sense the recycle is not there. So this fraction is 0. The entire inlet is the entire outlet for the plug flow. So when there is a plug flow, what does that mean? The recycle is 0. But now what will happen when R is infinite? When R is infinite, less fraction of it is going here. More fraction of it is almost recycled here. When R is infinite, what will happen is this particular plug flow reactor, though we assume that plug flow there is no mixing, because of the recycle, this plug flow reactor converts to a CSTR. So for a design design of this recycle reactors, you get one expression, big expression, which will be in terms of R. From that expression, if you substitute R is 0, you get a plug flow design expression. And if you substitute R is infinite, you should get CSTR expression. So recycle reactor is neither a plug flow reactor nor a CSTR, right? So with that, you remember that the final form of the recycle reactor will have in terms of R, and if you substitute R is 0, that is there is no recycle, then what this recycle reactor acts like a plug flow reactor. So it should, your design expression should come as plug flow reactor, and where R is infinite, the design equation of the recycle reactor to turn as a CSTR, because everything is recycled. Therefore, there is a mixing happening here. Therefore, the performance of a recycle reactor will be like CSTR. That we will see, right? So let us see the terminologies here. I'll just remove this so that it will be easy for us to discard it. Again, I'll put it. So why recycle reactors are used? The recycle reactors are used when the reaction is autocatalyzed. This is a very important point. When the reaction is autocatalyzed, that is some of the product or a few, the product itself is acting like a catalyst. You know, A plus R gives R plus R. A should give R, but R itself it won't form. Some of the R should be present, just like a curd example. If you want to make curd, you should add some curd into the milk, then only curd will come. Without curd adding, you won't get the reaction of curd from the milk, right? So autocatalyzed reaction is like that, right? So if very lot of autocatalyzed reactions, they use this recycle reactor. One more is, it is necessary to maintain nearly isothermal operation of the reactor. So one more very important point, the disadvantage of plug flow reactor is you cannot maintain the temperature, especially for plug flow reactor. That is one biggest disadvantage. Whereas CSTR, due to the mixed, you can maintain the temperature, but in PFR, you get different temperatures inside the reactor. That is one biggest disadvantage. So to eliminate that, generally a recycle reactor may be used. One more situation where you use this recycle reactor is to promote selectivity. Till now, I didn't mention what is this selectivity. Selectivity is nothing but if a reaction is giving you like this, if a product is, if a reaction is giving you, A is giving you R and A is giving you S, where R is desired and this is undesired. So selectivity is nothing but A should give only R, not S, because S is undesired. So the ratio of the formation of this to this is called as the selectivity. That is called as the selectivity. Whereas the yield is nothing but how much R is formed to that of how much A is consumed. That is yield, right? So that we will see in the third unit when we go for a different, what do you call, multiple reactions in series and parallel, and how different reactor combinations we have to use. So this selectivity, this term comes for the third unit, but here itself I'm mentioning when there is a multiple reactions, especially a parallel reaction, how much is the desired to that of how much is the undesired. That is what is the selectivity. You should get more selectivity, then only you get the desired component more. You don't want yes component, so we try to subsidize the formation of undesired component by increasing the desired component. That is what we call as selectivity. So if you want to get a more selectivity, that is more desired component, generally this kind of arrangement will go, right? So these are the three what you call situations where we go for a recycle reactor. One second, yeah. Yeah. Now let us see the terminology. What does this particular mean? Or let us go back to this third thing. What does he give here? Recycle reactor. He himself is giving just like that. Okay. Let me check in some other book. He is giving any background information. I just want to see. He is not giving any background information. So let us go back to this reactor. Now let us first discuss here and then go back to the previous one, right? So I hope everything is visible. So this is the fresh feed. This is the plug flow reactor. You are putting a plug flow and the product is being recycled. So without any terminologies, I will explain first, and then I'll take you to the this terminology, because this terminology is a bit difficult to understand. That is why I'm just not putting the terminology. Let us understand how the material balance you have to do, right? So in some cases it seems to be beneficial to return a part of effluent stream, either it is converted or the product stream. It does not mean that the recycle stream is only unconverted. Even some of the converted product also can be sent, right? So leaving the plug flow reactor to the entrance of the reactor, that is what is the recycle. In this case, the product effluent stream leaving the reactor is divided into two parts. Here at this point, this is the leaving stream and this is the recycle stream. So the product or effluent stream leaving the reactor, how much is being leaving inside the reactor is how much of the product is recycled plus the product leaving the reactor. So here leaving the reactor is nothing but how much is leaving this particular thing and how much is being recycled. So here there is a split. There are two outlets here. That is what he is giving you. So let us define a recycle ratio, capital R. What is capital R? The volume of the fluid returned to the reactor inlet to that of volume of the fluid leaving the system. So how much is being returned to that of how much is being leaving the system. This divided by this is called as the recycle ratio. So the recycle ratio ranges from 0 to the infinite, right? So that is what we assume. Let us, VF is the volumetric flow rate of the product leaving the system. Leaving the system is this particular thing. So then what will happen? If R is the recycle ratio, then the volumetric flow rate of the recycle stream. If this is VF and this will be R times VF, how much of it is going, sum of the fraction is going in this. Therefore, if this is VF, this becomes R into VF. That is what it is here. So if this is VF and this is R into VF, how much is this? This is nothing but this plus this. Therefore, VF plus R into VF, RVF plus VF is nothing but R plus 1 VF. So how much is coming outside the reactor is R plus 1 VF. That you remember, right? So let us go to this particular terminology now. That I'll project it this. You understood now? Let us understand the terminology first. So this is the inlet. If there is no recycle, let us assume this is the inlet and this is the outlet. Please listen carefully because there is some confusions how this terminology is attained. So please, when I am taking only the inlet, I am not taking this particular recycle. Initially, there is no recycle, right? As it goes on, the recycle stream will be increased. You are putting. So initially, let this is the inlet. There is no recycle stream. Fa naught is the flow rate. V naught is the volumetric flow rate, and Xa naught is the conversion. Conversion initially, A is giving you R. A is giving you R. There is no pen. So A is giving you R. So let us assume that A is giving you R. So initially there is no conversion. Finally, some of the converted product will be added here after the product is formed. Initially there is no R present in the feed. Therefore, XA is 0. So what is happening? Let you leave this particular for some time. Then this is a plug flow reactor. Let what is coming out, the concentration or the conversion is XA2. So here it is going, VF is going, the volumetric flow rate, how much is going is VF. So this XAF final conversion is nothing but what is there in XA2. That is what is here. So this VF, some of the VF is recycled back to the reactor. That is R into VF. So VF plus R into VF is nothing but the outlet of this. Therefore, R plus 1 into VF will be the outlet from the reactor, which is having a conversion of XA2. This particular R into VF, let it be V3, that is the volumetric flow rate, that is nothing but RV3. It is being added at or mixed at a point K. So this is unreacted and this is reacted, right? So this stream initially, yeah, this is unreacted and this stream is something reacted, some reacted, some reacted. So what is happening? Some unreacted, that is most of the unreacted A is added with reacted A or the product. Then what will happen? It is getting mixed here. Therefore, the product which is coming from this will not have this conversion at all because it is reacting with some of the product. Therefore, the conversion will change. Let it be XA1 here. The flow rate also initially it is V naught, but some of the flow rate is being added here. Therefore, let V1 be the flow rate. Like that again, volumetric flow rate is a V1 and a molar flow rate also this is Fa naught, and here also there will be something. Let Fa1 is the molar flow rate from K1 and Fa naught star is nothing but this particular thing is being changed. How much it is being changed, we don't know. We don't know how much is being changed because it depends on this R value. If R is 0, this flow rate is nothing but this flow rate. But if R tends to infinite, that is more of the product is being recycled, this gets changed. So that is why they are putting as Fa naught dash, right? So there should be some relation with this to this. That is what we will show you in the next slides. So there will be molar flow rate change, there will be volumetric flow rate change, and there will be the conversion also which is going to be changed, right? So rest of the thing is self-explanatory. XA2, what is being getting out, that is nothing but the final conversion, right? XAF is XA2. So let us go to the derivation now. We need to do a material balance around this. If you are going to do a material balance around this, what is the inlet to this plug flow reactor? This is the plug flow reactor inlet and this is the outlet. So this inlet, you should have XA1 to XA2. That is in the integral part. and your RA will be based on how much is the concentration at this particular stream, not at this particular stream, right? So how much is this particular thing we need to calculate, right? Yeah. Then let us go to the next slide. I'm just putting recycle ratio R is the volume of the fluid returned to the reactor inlet divided by the volume of the fluid leaving the system. How much is leaving and how much is recycled. This to this is called as a recycle ratio. Now R is 0. That means what? This R is 0. So nothing is recycled. Therefore, whatever is going out is nothing but a plug flow reactor. That is what we get. When R tends to 0, you get a plug flow reactor behavior. The recycle reactor behaves like a plug flow. And when R is infinite, you see here, this is infinite. That means very less stream is going here. More of the stream is going in this. That means that there will be a mixing. Therefore, your recycle reactor behaves like a CSTR design expression. We'll show how it is going to come, right? So these are very important in a recycle ratio. Recycle ratio turns to plug flow behavior when R tends to 0, and when R tends to infinite, your recycle reactor, the behavior, the performance equations turns to a mixed flow reactor. So let us see this expression. Now let us see this. I'll just go back. Let me give one small thing to you. Discard this. I'll just copy this and then try to paste here. Okay, you're not getting. Yeah, just to make my point clear, I just want that. Okay. Now you see the performance equation of PFR. This is nothing but this particular thing. Hope it is visible for everyone. I just turned it so that okay, let me not do that. Okay, let me shift it back. So let us put here so that I again can change it. Let us put here so that it will be easy for us. I will remove this. Now you see the performance equation of PFR. This is only the performance equation of PFR I'm considering. This is the inlet and this is the outlet. So performance equation of PFR, which is partially converted feed, because it is being mixed with the here the unreacted thing is mixed with the reacted. So what it will be, the performance equation V by Fa naught dash. We don't know how much it is. We will calculate how much it is. V by Fa naught dash, that is nothing but V by F is tau by Ca naught. Either you can write in terms of taus or you can write in terms of the volume. V by Fa naught, V by Fa naught is XA1. This is the conversion XA1 to XA2. But we don't know what is XA1. This is what is the unknown, right? So XA1 to XA2, dXA by minus RU. This is what we can write. But what is XA1? This is the biggest thing. How you calculate this XA1? This unknown. We don't know how much is being converted, is coming in there. And we don't know what is this also. To solve this equation, these two are the unknowns. Fa dash, F dash, E naught and XA1. So we need to give these unknowns in terms of the known parameters. So that is what we will be doing now. Now let us do what is Fa naught dash. Fa naught dash is nothing but, so you see Fa naught dash is A in the fresh feed. How much of the A is there in the fresh feed plus A in the unconverted reactor stream or converted reactor stream, whatever. Either this recycle stream can be converted or unconverted, whatever it is. Either of it, you can do it. So A in an unconverted stream recycle reactor or A in the fresh feed. So FA naught dash is nothing but this is FA naught. How much is here going? It is nothing but R into FA naught, because how much is going here? That itself is going here. So R times FA naught. So FA naught dash is nothing but R plus 1 FA naught. So FA naught dash is unknown, which you are want here. So we are writing in terms of the known. R, you know, because how much you are going to recycle, and FA naught is already known initially. So the unknown quantity you are writing in terms of the known. So we need to write for XA1. XA1 is again unknown. So how we will write that? That again, I'll put this up so that you can understand much better. Now let us write for XA1. So XA1 is nothing but how much is the conversion here? We know that XA is nothing but 1 minus CA by CA naught. But if you are writing for a gas phase reactions, then we can write a CA1 because there will be some concentration here. So that CA1 divided by C naught initially. So 1 minus CA1 by CA naught divided by 1 plus epsilon A CA1 by CA naught. If it is going to be liquid phase reaction, this will be 0. Therefore, you are left with this particular thing. But we are writing even for the gas phase reaction. That is why you are putting this particular thing. For a constant pressure, that is change in volume, especially for a gas phase reactions, let us write CA1. We know that CA1 we can write as FA1 divided by V1. But that is the molar concentration divided by the volumetric flow rate. Right? So this is the formulas. CA1 is FA1 by V1. What is FA1? Well, FA1 is nothing but FA naught plus FA3. FA3 is nothing but this. This plus this will give you FA1, right? So FA3 divided by V1. How much is this V1? Is nothing but the volumetric flow rate here plus the volumetric flow rate here. That is what? V1 naught plus R times VF. We know that FA naught. What is FA3? FA3 is nothing but R times FA naught into 1 minus XAF. That we can write, right? Because F or C's you can write. CA is CA naught into 1 minus XA, or FA is FA naught into 1 minus XA. FA naught is into 1 minus XA is nothing but whatever is the final conversion, right? So this thing is the difficult thing to remember how you are writing. Then V1, V0, R times VF is nothing but again V0 into 1 plus epsilon A XA. We know that volume change V is nothing but V0 into 1 plus epsilon A XA, right? So if you rearrange this, CA1 is FA0 common, V0 common. So FA0 by V1, it becomes as CA0. Like CA1 is FA1 by V1. So FA0 by V0 is nothing but CA0 into 1 plus R times 1 minus XAF by 1 plus R times 1 plus epsilon A XA. So if you expand this particular thing, CA0 into 1 plus R minus R XAF, I'm just multiplying this, right? Yeah, this particular thing, right? So shall I go for the next slide? Any doubt in this? Yeah. Any doubt, ma, here? This is one important thing what you are doing. This is the main important equation which you are writing. This somehow you remember, or if you can remember this terminology, then you can get it, right? So CA0 into this particular thing. Now I'll do some manipulation in such a way that I get a simple equation. Can I go for the next slide, ma? Yeah, some of you can tell.
Yes, sir.
Yes, sir.
So I'm going for the next slide. So now you see, this is CA0 and CA1. So I can take CA0 common, and then I can write CA1 by CA0. That is what I'm doing. CA1 by CA0 is this particular thing. I'm just taking this down, or right, this particular thing. down and this side, right? So CA1 by CA0 is this. Now substitute this particular CA1 by CA0 in 3. What is 3? This CA1 by CA0. XA1 I need to calculate, the unknown. So CA1 by CA0 already we got here. This you substitute here. This is the biggest thing because this terminology you substitute, that is what 1 minus R, 1 minus CA1 by CA0 divided by 1 plus epsilon A into CA1 by CA0. So patiently you take LCM, denominator is same for both, so you can cancel out. The numerator will be 1 times this minus this, and denominator will be 1 times this plus epsilon A into multiplied this. The denominator get cancelled out. And if you take all R terms to one side and all epsilon A to one side, so you have to do this, some things will get cancelled out. So you have to write in such a way that XA1 is R times 1 plus, again I repeat to you, from this step to this step, there is a huge calculation involved. You won't get immediately because in the numerator and denominator, you have to add some terms and then subtract some terms to give you this final form. That I will show you here. It's not that easy. Again, I'm telling you, it's not that easy. You can see here, this is the expression which you got. I'm just putting this final form. How you are getting this final form? Now you see 1 plus this is this, minus you multiply, here 1 into this you multiply, and again epsilon A you multiply with this, because this denominator and this denominator get cancelled out. So you see 1 plus 1 minus 1 cancel out, R minus R cancel out. So what is left in the numerator is R epsilon A XAF plus R XAF. So you are writing R, taking it common, 1 plus epsilon A into XAF you are writing. The denominator you see, what gets cancelled out? Nothing is getting cancelled out. I think 1 plus R, this particular thing, 1 plus XA, all that. So what you do is 1 plus XA you take common. This 1 plus XA, this is one term. Rest of the thing is R is there. I think there is something which get cancelled out. R sigma A XAF plus and minus. So these two gets cancelled out. So 1 plus epsilon A, R plus R epsilon A is R you take common, 1 plus epsilon A you get. So if you take 1 plus epsilon A again common here, what will happen is 1 plus R into 1 plus epsilon A. That is what you put. Correct, ma? Any doubt? Then this epsilon A, 1 plus epsilon A, 1 plus epsilon A get cancelled out, and you get XA1 is R by R plus 1 XAF. It's a beautiful equation. This is a beautiful equation. Any doubt, ma, here? Just some feedback. Yeah, this is simple doing this LCM and then cancelling out pluses and minus and writing in terms of what do you call some terms where something get cancelled out, numerator and denominator. Yeah, I'm writing like this so that 1 plus epsilon A, I think you can cancel out. So you are left with XA1 is R by R plus 1 XAF. You know what is XAF? So this XA1 depends on the recycle ratio. That is what is understandable from this. That is what is understandable from this. I'll just what happened? Blow it up. Okay, what? Yeah. So that is what I'm just trying to get. This is a beautiful equation. This is a very important equation. XA1 you are getting in terms of, which is XA1 is unmeasurable quantity. You are getting in terms of measurables. You know what is the recycle ratio, what you are going to send. So XAF, you already you know what is the XAF you are expected. So based on how much recycle you are giving, your XA1 will change. Any doubt in this, ma? So if you take your design expression, I'll just re-go to this, discard, and then this I'll delete. I don't want. Now I again go back. So this is the expression which I am bothered. This is the expression which I am bothered. So in this is the performance equation of a recycle reactor or a plug flow. So in this is unmeasurable and XA1 is unmeasurable. So I calculated what is unmeasurable here in this and what is unmeasurable XA1 I again calculated here. Now both you substitute in this expression now. This is first expression. Unmeasurable quantities I substituted back. So then what will happen? FA dash is nothing but V by FA naught into R plus 1 is equal to integral R by R plus 1. This is the XAF to the XAF dXA by minus RA. This is the performance equation of this fellow. What is that fellow? Recycle fellow, right? Recycle fellow. This is the performance equation, right? Any doubt in this? Any doubt in this? Now let us watch the fun, right? So be prepared to watch the fun. Now, what is this I told? When R is 0, it should behave like a plug flow equation. What is the plug flow equation? V by FA naught or V by F is nothing but integral 0 to XA dXA by minus RA, correct? That is what you should get. So what is the performance equation here? Recycle ratio is 0. Hey, whatever. Why I'm not getting the power? 1 second. Yeah, this writing on it becomes very difficult. That's why some subjects we cannot teach online. This subject should be taught on the board. Then only I can understand what whether you are able to. So V by F should be equal to integral 0 to XA dXA by minus RA. This is the performance equation it should result. Whereas when R tends to infinite, you should get V by F should be equal to XA by minus RA. This is the thing which you should get. We'll see whether we are getting this expression or not. This is the expression, right? Now substitute R0. Yeah, take a book, take your notebook. I don't want to show the next slide. Take your notebook. Yeah, put R is 0. What is happening here? When R is 0, what is on the LHS? V divided by FA naught into 0 plus 1. That is nothing but FA naught. Correct. Is equal to integral. What is in the integral? R by 0 divided by 1. Right? So R is 0 divided by 1. 0 divided by 1 is nothing but, what is 0 divided by 1? What is 0 divided by 1? Is 0, right? So 0 into XAF is nothing but 0. The lower limit is 0. The upper limit is XAF. This is nothing but dXA by minus RA. So absolutely fine. Very good. So when R tends to infinite 0, you are getting a plug flow equation which you expected. Correct? Correct, ma? Yeah, I just want your feedback now.
Yes, sir.
Correct? Now, what I'm going to tell, it will test your mathematical ability now. You might be expecting what is my next question? What is my next question? What should be my next question? Yeah. This equation, when R tends to 0, you are getting a perfect plug flow equation. Correct? That means when there is no recycle, your FA naught becomes your FA1 or whatever it is, because there is no this particular stream. So you are left with FA naught or this particular thing. XA naught also will not come because this is the same thing. XA2. That is what 0 to XA2 you are putting. Absolutely correct. Now my question, the second question. When R tends to infinite, yeah, what is going to happen? Just imagine V by Fa naught R plus 1, infinite plus 1. How much it is? How much it is? Infinite. So V by infinite, R Fa naught into infinite is, yeah, what is the limits now? R is infinite.
XAF to XAF.
Infinite by infinite, how much it is? Okay, you take it out 0. XAF to XAF. XAF to XAF, dXA by minus RA. What does that mean? What does that mean? Because you know that when there is a R is infinite, that means what? Entire thing is being recycled. There is no thing here. Therefore, your plug flow should convert to the CSTR design expression. But whether CSTR is coming here, whether CSTR is coming, that is what a big question. Whether CSTR is coming. So put XAF here, put XAF and XAF dXA divided by minus RA. Yeah, tell me. Is it this particular thing CSTR? So now this is like an assignment or whatever you name. The fellow who does this derivation and submit to me, there I tell that they are pistu in this mathematics, right? You call this pista, right? In Tamil, pista means someone who tells that I know everyone, right? So is no way chemical engineering is involved here. It is just a mathematical. It tests your mathematics. What do you call this? Integration of your mathematics or mathematical fundamentals. How you convert this equation when R is infinite to this particular equation. This is what I want. Yeah. I again open question here. In no book will give you. You see any book. This is the 11 spill which I am showing you. No book will give you. Just he'll give you if that particular thing is going to be 0. Where is it? Yeah. This is the equation. From this equation, when R tends to 0, you are getting this. When R tends to infinity, you are getting this. That is what they will give. But how it will come, no one will give. Either this book or even this book. This book also he will never give. This book also he will never give. He himself is giving. That's all. The final expression. No book will give you how you are getting this expression. So it is whatever you name, assignment or whatever way you take. I don't want call this as an assignment, but yeah, try to get it right. You discuss with your friends and try to get it right. So before we'll continue that derivation, it is not yet over. We'll just see some more part, right? You understood the question what I am going to ask? Emma, you understood or not? What you should do, right? So this is the expression. Now R plus 1 is common, so you can put this side. That is what is putting. V by Fa naught is R plus 1 into R divided by R plus 1 XAF dXA by minus RA. This is for any epsilon A. There can be expansion 0 or anything. The above equation is the desired performance equation for recycle reactors applicable for any kinetics. Any can be your reaction rate for any epsilon A or XA is 0. So when epsilon A is 0, you are left with this particular equation. This is for liquid phase reactions tau by CA naught or V by FA naught is R plus 1 into integral this particular thing to this dCA by minus RA when epsilon A is 0. And this particular thing, let it be this equation. B by FA naught is this, right? So what I am asking you from it is, this is for any epsilon A. When you substitute R is 0, you are left with this particular thing. When R tends to infinite, you are getting this expression. I am asking you from this equation, how you get this equation, right? So that's up to you. You come out with a good answer. Again, I tell you, if you are not applying your mind and if you start doing this derivation, you go to more than some 5 pages, 6 pages, but answer will not come. The answer is only one step. I am giving you the hint also. The answer is only one step. That's all. But you should apply your mind. If you are not applying your mind, if you blindly go with the normal integration and differentiation, whatever you know, even 10 pages of whatever you do, you will never get this. The answer is just one step. From this to this is just one step, right? So that you keep in mind before you do the derivation. Okay. So again, if you want to have epsilon A 0, then you can get k tau by R plus 1. It depends because you are substituting RA as first order, second order, and different epsilon A. These are all just the extension of it, but you try to remember this equation, right? And how you are getting from this to this is what is the important thing. This is going to be a 12 marks question, which they can be asking. Derive the performance equation of the recycle reactor. The recycle reactor performance equation is V by FA naught is R plus 1 integral R by R plus 1 XAF to XAF dXA by minus RA. One important thing is here is the variable. R is the variable which is coming in the lower what do you call interval. The derivation of it, the integration, the lower integral is nothing but the variable. I'll give you some more important information. Now this R plus 1, you split this R plus 1, what will happen? If I write this expression as a full form, how I have to write? I'll just write here. Now you see V by FA naught is R times integral R by R plus 1 into XAF. This is XAF dXA by minus RA plus this 1 times multiplication is again integral R by R plus 1 into XAF Yeah, sorry for the extra lines. I think this pen I'm not holding it proper. Minus RA. So you get two terms, right? You get R term and one term, right? Is that correct? Now can we draw a graph? The graph is what is important. I'll show you in the graph now, right? Now let us take this. What is the expression? What is the expression which we got? V by FA naught is R plus 1 integral R by R plus 1 XAF to XAF dXA by minus RA. This is the performance equation of recycle reactor. You can club this, you can expand these two, right? So let us do that. Now, when R is infinite, when R is 0, what is happening? When R is 0, entire thing is 0. So you are left with only this particular thing. Am I right? So that is what? When R is very small, you are multiplying R plus 1, right? When R is very small, So this particular thing, this is XAF. I'm taking this as R and this is 1. So what is the one component? One component is nothing but what do you call this area under the curve is nothing but PFR, right? The one component is nothing but PFR. R is very small. Therefore, to go from 0 to XAF, you are splitting from 0 to R, particular thing, from here to here. So from here to here is a plug flow reactor, and this added to it is nothing but the entire volume required. Am I right? So when R is small, very small, it is almost the area under the curve. Therefore, you are getting a volume of the plug flow reactor. How to calculate the area under the curve? Earlier itself I told you can take what you call midpoint of this and then take a rectangle. You find out the area of a rectangle. So this is not there, this is there. So you are assuming this is equal to this, and then you can calculate the area of a rectangle. So this small thing is the R component, and this big thing is the big component. The entire thing will become as R plus 1 component. That is this, the volume required for the entire thing. Now what will happen when R is infinite? When R is infinite, that means infinite plus 1 is very small. That is what? One component is very small. R component is very big. R component is very big. You know that the area is the rectangle. That is what you tell. R plus 1 is R plus 1. So area under the curve or the rectangle. This is the big rectangle which will give you the volume. So for a small recycle, we can understand from the graph itself that the area of a recycle stream is nothing but the area under the curve. Whereas for the big one, so you have to have this entire thing. Therefore, you can keep that the area of a rectangle is nothing but the area of the recycle reactor. So for a large recycle stream, you know that the when R is infinite, your performance equation turns to CSTR. That is what it is shown here in a graphical way. Does it make sense what the explanation I'm giving you? So from the equation part, we are getting the design equation of PFR and MFR. Even from the what do you call graphical part also, it is understandable that when R tends to 0, your performance equation, mixed reactor performance equation goes to a PFR, and when R tends to infinite, your performance equation goes to a MFR. Right? This again, you want to draw a graph between C by C naught to tau R by tau P, that is nothing but recycle reactor tau to that of plug flow, or V volume of recycle to that of volume of plug flow. This R is 0. When the R tends to 0, your ratio of taus will become this particular thing. In the y-axis, you are writing C by C naught. This is for the first order reaction. As R increases, as the R, that is the recycle stream increases, your R is infinite, your mixer reactor, the what do you call tau is a gradual this particular curve. So it goes and touches this particular curve, and this is for different k taus. K tau is nothing but the Damkohler number. Earlier itself I told, more the Damkohler number, more will be the conversion. That is what k tau 1, k tau 2, k tau 5, k tau 10, more k tau this particular thing. This is for again the second order reaction. For a second order reaction, you know that k tau into Ca naught it will come because the order is changed. So again here k tau Ca naught is 1 based on this, and this is for the R is 0, and R as the R value changes, you are going and getting a mixed reactor performance equation. The ratio of this particular either taus or the volumes. This is the comparison of performance of a recycle reactor with plug flow for a elementary second order reaction. For a second order reaction is this, and for a first order reaction is this, because as the order changes, your performance of this particular thing will change because the kinetics are changing. Am I right? So that is what I want to tell. This already we discussed for a autocatalyzed reaction. You know that it starts with somewhere here. The rate increases and then falls down. So the progress of reaction is going to be like this. If I put 1 minus RA, there will be a minimum where your rate will be maximum. You have to find out how much is the maximum this. This you can get when you differentiate this equation. You need to have where is that point. So for that point, you need to differentiate this equation and then substitute to 0. Then you get the maximum value. That is what is the difficult one. Because how you differentiate this equation, how you differentiate this integral equation, the integral again, the lower limit is a function of R, which is a variable. Yeah, very difficult. It's not that easy to differentiate this equation. A differential of an integral. Again, test your mathematical ability. Yeah, that we will see in the next class, right? That is what we are trying to put the differential this particular thing by dr with respect to r. R is the recycle ratio. So differentiating this with respect to r and equating to 0, you get this value somewhere where the my 1 by RA is minimum. That means that your rate is maximum. That we'll see in the next class. It's not that easy. A differential of an integral with again r, the variable itself, is going to be very tricky. For that, you need to have this operation requires the differentiating under an integral sign, which a differential for this particular problem. The theory of calculations, this is the solution. Don't ask me how you are getting this solution. You go back to your mathematical thing and then find out, right? So using this formula, we need to differentiate this and equate to 0. That we'll see in the next class. And then once you differentiate it and equate to 0, we can get where is the maximum R which is being present, how much is the maximum inside this what do you call mixed react or recycle reactor. That we'll see in the next class, right? So with that, we'll try to wind up in the next class. And if you want any problem, we'll try to solve with this recycle reactor, right? Yeah, because it's already 11:57. I don't think I can complete this derivation. I'll see in the next class. Yeah, any doubt? Again, a lot of doubts you will get, especially if you can understand this. Yeah, I know where is the difficulty even without you telling. I know you will get a lot of doubts in this, but you never mention anything. But I know as an average student or as for a student to understand this particular thing is not that easy. What is this R? What is this one? What is this one? And what is this one? Try to visualize. If you're not getting that visualization, tell to me again, I will explain. I know people will get doubt here. Not only people will get doubt there, even here how you are going to get. It's not that easy. Understand? Yeah. Any doubt now? I just want to wind off today.
Sir,
Yes. Yeah.
I saw a question in that assignment, sir.
Hmm.
They were having a CSTR and they introduced the recycle stream. They asked,
Yes.
will it affect conversion?
Yes.
But the answer was it won't affect conversion, sir.
Hmm.
But for this same flow rate, if we introduce recycle for an CSTR, won't the concentration of A decrease and the conversion will also decrease?
Here one important thing is in a recycle reactor, we are assuming it is plug flow initially. Right? So initial thing is plug flow, and then we are introducing a recycle stream. Therefore, the plug flow changes to recycle because plug flow there is no mixing, whereas in recycle reactor there is a mixing involved in plug flow. But if you are taking a CSTR expression here instead of a plug flow, CSTR itself is there is a mixing. So I think that should be the answer for you, whatever question you asked. Yeah, now think about what question you asked. One answer should be there. You are telling the conversion won't change or something like that. Yeah, think about it. Did I answer your question, or did I make you still confused?
Confused, sir.
Yeah, I know. It will be a lot of CRE is like that, confused reaction engineering. That is why people call C as confused. You have to have a very good understanding about not only understanding, visualization, what is happening. Yeah. Now I gave the hint to you. Based on that, you just try to visualize, and then if any difficulty is there, you let me know. Yeah. Good question. Yeah. Any other? You get n number of doubts. I know a lot of silly questions also will come. Maybe you are not interested to ask it, but really there will be a lot of silly questions. Really true. Because when we went in IIT Madras, when the professor is teaching this particular topic, he taught for around 6 to 7 hours. Not because there is something in that, because the people are asking some silly questions, and professor is having a lot of patience to clear all that. Really, a lot of silly questions can come. Really, especially in the recycle reactor. True. Any other? Any other? Yeah, for a BTech point of view, I just didn't go much in detail. I can agree to it because I need to cover the syllabus, but some people are interested. I can go a bit much deeper inside to give you what is the visualization, but you can learn in MTech when you go. Yeah. Shall I stop with this, or still you want some more clarification or something like that? So with that, I think I stop the recording. I think as usual, you don't want to ask any questions.